Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
High-threat volcanoes, Mount Hood, Mount St. Helens, and Mount Rainier.
What if everything we thought we knew about the Pacific Northwest volcanoes was wrong? Mount Rainier, Mount St. Helens, and Mount Hood have stood as isolated giants, each with its own history, threats, and risks. But what if these volcanoes were in fact connected deep below by secret pathways of molten rock, a hidden network that could link their fates? Scientists have long taught us that each mountain is its own ticking time bomb, but on July 3rd, 2025, that assumption came under startling new scrutiny. USGS satellites returned imagery showing not just activity inside one volcano, but indicators of movement between several. The emerging data outlined anomalies stretching from Rainier to St. Helens and onward toward Hood, a potential network previously invisible, now drawn in signals across the range. Within hours, emergency phone lines lit up. Scientists at the Cascades Volcano Observatory pored over their screens, grappling with the enormity of what they were seeing. The patterns they observed weren't fleeting. These were signals demanding attention. And so, for the first time in living memory, the USGS issued red alert warnings for multiple Cascade volcanoes at once. Are we seeing the birth of a volcanic chain reaction that could shake the entire Pacific Northwest? Signals in the deep. Satellite detects a magma network. This story began with a survey and a race to outpace the next eruption. Satellite reconnaissance, especially using InSAR radar technology capable of detecting tiny ground movements, was intensified across the Cascade Range. This time, the data defied standard patterns. Radar pulses returned images with new clarity. Beneath the snowy summits of Rainier, Hood, and Helens, something was shifting beneath the crust. The first sign appeared as a band of uplift marching southward, starting near Rainier's southern flank, traversing the valleys beneath St. Helens, and continuing toward the foot of Hood. In previous years, such motion was attributed to more mundane processes, groundwater fluctuation, glacial rebound, or seasonal snowpack loading. But this sequence of aligned movement was different. It didn't stop with one volcano. It connected them. The evidence pointed toward magma, molten rock accumulating under the crust and exerting pressure in a linear path. It wasn't just pooling beneath a single cone. It was moving, traveling. Thermal imaging provided further support. Unusual heat signatures clustering not only beneath each volcano, but also along the axis tracing between them. Gas sensors picked up spikes in sulfur dioxide and carbon dioxide, not just at mountain vents, but at sites in the valleys and forests that stretch between their bases. These gases, often emitted from magmatic sources, signaled something far less stable than shifting ice or groundwater. Then came the tremors. The seismic network recorded a consistent pattern. Low-frequency earthquakes, often associated with magma transport, began to march from Rainier to St. Helens and then southward. Each tremor echoed along the newly detected path of ground deformation and heat. While the past had seen isolated swarms and occasional rumbles, never before had so many distinct data sets. What if the Cascades aren't a chain of isolated peaks? This is no longer a hypothetical. Volcanologists now suspect a deep magmatic connection may exist, one that spans miles beneath the Earth, threading major volcanoes into a single, breathing entity, a sort of molten corridor, dormant for millennia. Geological records hint this wouldn't be unprecedented. Around 15 million years ago, during the Columbia River basalt eruptions, this is no longer a hypothetical. Volcanologists now suspect a deep magmatic connection may exist, one that spans miles beneath the Earth, threading major volcanoes into a single, breathing entity, a sort of molten corridor, dormant for millennia, but now flickering back to life. Geological records hint this wouldn't be unprecedented. Around 15 million years ago, during the Columbia River basalt eruptions, vast volcanic systems blanketed parts of the Pacific Northwest in lava flows from fissures, not cones. If this newly observed pattern is connected to a similar deep crustal process, one hidden for eons, then the threat extends far beyond singular eruptions. Instead of monitoring isolated calderas, the scientific community is being forced to reconsider the very nature of volcanic threat in the Northwest. Could pressure beneath one peak trigger another? Could a cascading event triggered along this magmatic corridor unleash eruptions in sequence? Researchers are racing to understand whether this is a temporary fluctuation or the early stages of a regional reawakening. Some suggest it could be the result of crustal stretching. Others theorize it's the upward push of a new mantle plume. Either way, it's a signal no longer being ignored. The land was not just rumbling, it was pulsing, breathing, communicating, if only we know how to listen. And if the Cascades are speaking in magma and steam, the only question that remains is, are we prepared for what they're trying to say? A vein of fire, the magma tunnels unveiled. When the USGS made its announcement, it was historic. In measured language, the agency confirmed satellite evidence of what appeared to be magma channels, sometimes described as tunnels, running beneath the Cascade volcanoes. Red alert warnings were issued for multiple peaks in response to a confluence of signals suggesting a dangerous phase of unrest. But what is a magma tunnel or channel? Beneath most stratovolcanoes, magma pools and chambers, blisters of liquid rock rising from the deep mantle. These reservoirs are usually thought of as isolated, feeding individual eruptions through vertical pathways to the surface. But the new satellite data illuminated something more intricate: branching anomalies aligned with thermally active and seismically disturbed zones, giving the appearance of molten rivers threading between volcanic systems. Using InSAR satellite radar and magnetotelluric imaging, scientists traced these subsurface anomalies snaking through the crust, some as shallow as 5 kilometers, others deeper than 20. The channels weren't static. In fact, some sections pulsed with heat and conductivity, indicating molten movement or pressure buildup. They seemed to arc beneath known fault lines, wrapping under Rainier, curling around Mount St. Helens, and extending toward the flanks of Mount Hood. This discovery changed the conversation. If pressure moves along these subsurface networks, then unrest in one chamber might communicate with another. In theory, pressure building beneath Rainier could force magma not just upward, but along these newly illuminated paths toward St. Helens or Hood. This isn't science fiction, it's a documented geological process known as lateral magma intrusion. It's rare, but not unheard of. And here, it may be real. Could the Cascade Range be less a series of isolated volcanoes and more a single, sleeping organism with nerves made of molten rock? That was the question, now gripping volcanologists. Volcanologists began a new round of modeling to gauge the possible threat. Could the fissures and channels join these volcanoes as a system capable of synchronized eruption? Could pressure shifts at Rainier set off events at St. Helens, or vice versa? The stakes were enormous, and the urgency of the moment clear. Gas emissions were rising, not just from the summits, but from forested valleys in between, suggesting venting from pressure traveling these underground paths. Earthquake swarms began appearing in locations without known volcanic structures, lining up along the newly revealed channels. And thermal satellites picked up heat anomalies emerging in unexpected spots. The chain reaction threat, lessons from the past, and signals for the future. Volcanoes do not always obey simple rules. Cascading eruptions have been theorized, but most monitoring and safety protocols rest on the premise that Cascade volcanoes act largely as independent hazards. Yet geology is full of surprises. There have been rare instances worldwide where signals have migrated across distances, or where activity at one volcano precedes disturbances at another. Experts recalled the 2011 Nabro eruption in Eritrea, where a pattern of rhythmic tremors across the region foreshadowed disaster and were later interpreted as evidence of wide-area magmatic movement. Now, attention is fixed on the Pacific Northwest, where signals appear synchronized as never before. Minor quakes that rattle Rainier seem followed by low-frequency tremors beneath Hood. Gas spikes and surges in heat mimic in sequence across the network. While causality is not proven, the correlation is enough to prompt heightened concern. Beyond the mainland, there's the added variable of axial seamount, a submarine volcano just off Oregon's coast, the most active known volcano in the Pacific. Scientists have warned of another likely eruption there in 2025, and its tremors sometimes bear subtle correlations to onshore volcanic activity. Is it a coincidence that, both on land and at sea, America's fiercest volcanoes now appear restless at the same time? Or could the deep forces pressurizing one sector affect the wider region? The nightmare scenario: when mountains move in unison. Picture the moment. Deep beneath Mount Rainier, rhythmic quakes build, first almost undetectable, then rippling through the region. The surge is not limited to Rainier. Soon after, sensors under St. Helens report corresponding tremors, and not long after, Hood's ground movement intensifies. Thermal satellites track expanding patches of heat, not only at summits, but in the corridors between. Streams turn cloudy, sulfur odors intensify. Glacial snow melts prematurely, feeding silt-laden rivers. It's not just the simultaneity that alarms authorities, but the apparent coherence, as if these ancient peaks are communicating, each disturbance priming neighboring systems. In the worst-case scenario modeled, an eruption at Rainier releases pyroclastic flows and triggers major lahars, deadly mud flows, toward towns like Orting, Puyallup, and Tacoma. Within minutes, response teams scramble, but the margin for safety is razor thin. Almost simultaneously, Mount St. Helens begins to erupt, its crater sending ash skyward and unleashing pyroclastic surges. Hood, quiet for centuries, then shows rapid deformation. Part of its northern flank distorts. Hot spots appear. Meltwater surges through river valleys. In every city under volcanic shadow, residents are forced to react, often with little warning or certainty, which peak will erupt next, or whether the sequence will end with 3 eruptions or cascade into more. The red alert, a warning, too big to ignore. In the United States, a red alert from the USGS signals the highest level of volcanic hazard. It means a major eruption is imminent or already occurring, and that emergency protocols must be activated without delay. On July 3, 2025, red alerts for Rainier, St. Helens, and Hood launched a region-wide emergency response. Within minutes, emergency operations centers across Washington and Oregon coordinated drills and responses. The hardest reality: there is no way to predict with certainty which volcano will erupt first, whether all 3 will go in rapid sequence, or if aftershocks will propagate further down the range. The region's highways rapidly filled with vehicles as residents weighed whether to stay or flee. Engineers worked to secure power lines and critical infrastructure. Scientists, meanwhile, worked feverishly to understand the new signals. Satellite and seismic data streams were reviewed hour by hour for any indication of which volcano would move first, whether magma channels visible in remote sensing were expanding, and if the region could hope for a pause or would be forced to respond to a full sequence of eruptions. If data could provide certainty, perhaps the danger would soon ebb. But at this stage, all that was clear was that the risk had entered a new and unprecedented phase. Echoes in the earth, the pulse of a hidden system. As the crisis unfolded, a curious phenomenon was noticed: repeating low-frequency signals, dubbed simply the echo, detected by seismologists across the region. At roughly regular intervals, These vibrations were registered at monitoring stations from Rainier to Hood and farther, their source elusive and their meaning uncertain. Some theorized these echoes were a sign of shifting magma, perhaps moving through the newly revealed channels. Others suspected the signals reflect harmonic tremor, continuous vibration caused by movement of fluid magma, a known precursor at times to eruption. Triangulation provided no clear epicenter, and occasionally the signal appeared strongest offshore, near the restless axial seamount. Theories proliferated, but with evidence mounting that these signals travel the length of the proposed magma network, the echoes became an added focus for experts anxious to predict the system's next move. The uncertainty felt eerily reminiscent of past volcanic crises. Signals once dismissed as anomalies now commanded close scrutiny, as even minor tremors could signal a larger, system-wide event. A web of danger, the towns beneath the mountains. For those living in the shadows of these volcanoes, the consequences of a potential multi-peak eruption are impossibly real. The threat at Mount Rainier is especially dire. If its magma system fails, massive lahars can form quickly and race downstream, threatening the towns of Orting, Puyallup, and parts of Tacoma. Even with sirens and pre-planned evacuation routes, response time may be as short as 40 minutes. Lives would turn on the precision of alerts and the speed of movement. Mount Hood poses a different suite of risks. While not as recently active, a sudden release of magma or a partial flank collapse could generate strong lava flows, pyroclastic surges, or secondary lahars. These dangers are compounded if magma or pressure can travel along new underground pathways, potentially increasing the unpredictability of eruption sequences. Every scientific update, every emergency drill, every siren test becomes crucial in the face of such danger. And with signals still suggesting subsurface movement, attention across the Pacific Northwest remains fixed not just on the known volcanoes. The Ring of Fire awakens. What comes next? The Cascades are only a segment of the Pacific Ring of Fire, a vast arc of volcanoes and faults circling the ocean basin. As the American West faces its current challenge, it's worth noting heightened activity elsewhere as well. Axial Seamount, offshore Oregon, and the most active submarine volcano in the North Pacific, is closely monitored. Researchers recently sounded alarms about a probable eruption in 2025, echoing underwater activity before. Some of the region's seismic signals have coincided with unusual readings at axial, though the level of coupling between onshore and offshore systems remains under investigation. Elsewhere, volcanoes in Alaska and the Aleutians, as well as in Hawaii, have shown new unrest. It raises questions. Are these events separate, or do they hint at a broader process? One where magma movement and tectonic strain are influencing multiple systems across wide distances. Locally, experts now ask whether other Cascade peaks, Glacier Peak, Mount Baker, the Three Sisters, might be linked by the same or similar subsurface channels now suggested between Rainier, St. Helens, and Hood. Satellite and seismic monitoring have been expanded to check for similar uplifts, heat patterns, and gas anomalies at these other volcanoes. As the red alert endures, only time will tell whether the current crisis will pass with minor eruptions or mark the start of a new, more interconnected period in Cascade volcanism. Waiting under the shadow. And so, the region waits beneath these powerful mountains, awe and fear in equal measure. For many, the volcano's snowy crowns have long been emblems of beauty and reminders of nature's force. Satellites continue to watch the rain, ground-based sensors record every quake, and scientists model hundreds of possible scenarios. Community drills repeat. For those living in the shadows of these volcanoes, the consequences of a potential multi-peak eruption are impossibly real. The threat at Mount Rainier is especially dire. If its magma system fails, massive lahars can form quickly and race downstream. The red alert persists. In town halls, on local news, talk circles back to the crux questions. Are we on the edge of a chain eruption? Will the system fall silent again? Or is a unique, unprecedented event now starting to unfold? Nobody knows the ending. The Cascade Giants hold their secrets for now. The magma beneath them has proven more alive, more interconnected, and more mysterious than anyone dared believe. And so everyone listens, not only for the next siren, but for the next subtle signal from deep within the earth. Will the Cascades fall silent, or is their long-awaited answer now rumbling to the surface? Only time will tell. For now, we remain poised under their shadow, watching, warning, and waiting, connected, like the volcanoes themselves, by the web of fate that runs through the heart of the Pacific Northwest.